Hi everyone, my name is Evan Corville, and today I'm going to talk to you guys a little bit about ScramJets. Now, what is a ScramJet? A ScramJet is just a variation of your typical air-breathing jet engine. And side note, here is one of NASA's projects. They named it the X-43 plane, and it was capable of reaching speeds of up to Mach 9.2, which is pretty amazing. That's about 7,000 miles per hour. Now, before I start talking about scramjets, I'm going to show you guys how we get from a typical jet engine to a scramjet. So let's start with a turbojet. Now, in a turbojet, there's typically three stages. There's a compression stage, combustion stage, and an expansion stage. Now, typically for a turbojet, the operating range is about Mach 0 to Mach 3.5. Now, why is this? Well, when you get to around Mach 3.5, the aerodynamic forces, the drag forces, just by the engine, the fan blades, are just way too high to be able to overcome the theoretical maximum thrust. And also the temperature from the frictional forces that air traveling is fast. It's pretty fast. So what happens if we want to go faster? How do we do this? And the answer is, let's take away the moving parts. So if you take away the moving parts from a turbojet, you get to a ramjet. So, ramjet, the air comes in, gets compressed. Now the kinetic energy from the flow is what's used to actually compress the fluid in this engine. So as it flows from the compressor to the combustor. Now it's important to note here in a ramjet that in the combustion chamber, the air has to be slowed down to subsonic velocities for combustion to still take place. And then, as in the typical jet engine, expansion, and then we get our thrust. So what happens if we want to go even faster? Well, first off, ramjet operating range is about from Mach 3 to Mach 6. So what's the limiting factor in this? And to answer that, it's because we're still slowing the air down to subsonic velocities, and that's still creating a really high temperature and material limitations. We can't do that. So what happens if we want to go even faster? The answer to that is, let's not slow down the velocity of the combustion chamber to subsonic flow. Let's keep it supersonic. So ScramJet is a supersonic combusting ramjet. Now these things are pretty cool. So the typical operating range for a scramjet can be from Mach 6 to Mach 10 plus. There's actually, I was reading some papers, and there's theoretical calculations that these things can travel at velocities up to Mach 25, which is really freaking fast. So here's our scramjet. The kinetic energy from the flow is used to compress the gas, and then you typically add a fuel in here, and then the temperature and the pressure cause combustion. Now, to aid combustion, because this will be the equivalent of trying to light a match in a hurricane. It's just not going to happen. Typically, chemicals that spontaneously combust in air are mixed in with the fuel to sort of aid the combustion process. So now I'm just going to give you guys a typical thrust calculation. Now I'm going to use a turbofan because the data for scramjets is super hard to come by because it's all military research and classified. So it's really hard to find the pressure ratios across the engine and stuff. So we're just going to do a thrust calculation for the turbofan. So step one, control volume, draw your forces, and then now we just do a typical momentum equation. So we get our forces equal to the momentum exiting minus the momentum going in, plus the pressure difference from the air times the area. And this is a plane traveling about 30 meters per second and the exit velocity of the gas in is about 400 meters per second. And we get a thrust of around 17,200 pound forces. And this is typical for a 747 jet engine. So that was pretty cool. So some of the disadvantages of a scramjet are, the first disadvantage is, it requires a Mach number of about 5 to 6 for ignition. Now, why is this? Because, well, you need sufficient temperature and pressure for the combustion to take place. Second disadvantage is level flight is not possible. Now, the reason for this is that, you know, for the rate of fuel consumption to remain constant, you need a constant temperature and pressure in the engine. Now, the typical mechanisms that we use to do this in a typical turbofan, it's not possible with, you know, at these high velocities. So, and then you get a low thrust to rate ratio, and it's very difficult and expensive to develop and test. So, some advantages, you know, it doesn't have to carry an oxidizer, such as like a jet engine or a rocket fuel thing, and it's there's no moving parts, it's easier to manufacture, and possible and cheaper access to outer space. So, and a few applications, we'd be able to travel anywhere in the world within an hour and a half flight, and maybe able to replace a rocket stage. Cheaper outer space access. Okay. Any questions? Yes.
Can you go ahead and see the one that you showed the
C?
Yeah, with that. Sorry, it's good there. Okay, so does that piece move or is it stationary?
No, just a piece of metal.
Just stays there?
Yeah. And it's pretty cool.
Yeah. Okay.
But remember, air has to be coming into this around Mach 4, Mach 5
Right.
to be able to reach high enough pressure and temperature to combust the gas.
Okay.
Do they simply carry it up and drop it to free fall, and that's how it starts?
Yeah, well, typically, the tests that NASA were doing, they were bringing it up on like a Boeing 747. They were dropping it, and then they'd have a rocket that would accelerate to Mach 4, Mach 5. The rocket would detach itself, and then it would accelerate to around Mach 10 or Mach 12. But I think they were only able to like run these engines for about 10 seconds. Yeah, so there's still a lot of research being done. Any other questions?
Let's thank our speaker.